Hey everybody, welcome to today's lesson on plate tectonics. We're going to go through half of these notes that I would like you to bring up. They're attached to today's Google Classroom assignment. You should see them attached. Just click on them. You can either bring them up in a separate window, look at them when you need them. If you have a printer and ink, maybe print them out and read along or highlight where you think you need to highlight. So just watch this video. We're going to get through half of it with this lesson, and then we're going to have a lab about what's called the plate boundaries. All right, so I'm just going to go ahead and hit present here, and we'll watch the slideshow. So the first thing that comes up is this little video. I've actually played this before. I'll play it again in a minute, but I want to go over some of the notes first. So plate tectonics is the overall theory that explains continental drift, seafloor spreading, and earthquakes and volcanoes. If you remember, I've mentioned a few times that plate tectonics was called a building block or a stepping stone theory, and that you had a minor theory first called continental drift, and then seafloor spreading built off of that, and then eventually plate tectonics kind of brings it all together into one large theory. So this tries to explain continental drift, seafloor spreading, and earthquakes and volcanoes, which we'll kind of end the unit with. All right. So this theory states that the lithosphere, that's the land or the crust, is broken up into these giant pieces called the lithospheric or tectonic plates. The analogy I always like to give is a hard-boiled egg. Okay, now hard-boiled egg isn't a perfect sphere like the Earth, but you have a core, that's the yolk. You have the egg white, that would be your mantle. And then you have the shell, that would be your crust. Now, why do I like using this right now as an analogy? Because the way I always liked to break my hard-boiled egg is I always like to roll it. I always found the shell comes off easier that way. So let's imagine you had a hard-boiled egg and you began to roll it. What would happen to the shell? It would break up into lots of pieces. Okay? Where those pieces meet, that's where you can have the most friction and really the most movement, whether it's over or under. Okay? Now we got to take that analogy and relate it to Earth. Imagine all the water, all the dirt, all the trees and grasses and the rest of the vegetation was to disappear. What would the crust look like? It would actually look like a giant broken hard-boiled egg. You would see Earth's shell broken into pieces. And where those pieces meet, that's where you have your earthquakes and volcanoes. And we call that the plate boundaries. Okay? All right. So the lithospheric plates, they are floating on the asthenosphere. We went over that more than once already, and when we did the Earth's interior. Now, what's the driving force behind plate tectonics? So remember, Alfred Wegener couldn't come up with the force to move continents. And then we got these discoveries of the mid-ocean ridge and the trenches, which led to the seafloor spreading theory. And then what happened is we got heat readings. And we discovered that we already knew there was volcanoes and that it was probably hot down there, but we didn't know how much the heat was circulating. And we call these convection currents or convection cell. So there's these giant circular flows of heat. Right? And I actually played this for you before. I'll play it again. You can enlarge it on your screen if you want.
It happens because hot rock rises, heated by the Earth's core. Near the surface, the rock spreads in two directions and goes sideways. It begins to lose heat. Eventually, the much cooler rock sinks back down. Through this spreading process, the Earth's crust is very slowly dragged apart, and it's this that ultimately causes the continents to move. Where the plates collide, the rock on the seafloor containing carbon from the dead plankton is carried deep into the Earth. As it descends, this layer of rock is heated. so the rock melts, releasing carbon dioxide. And gas is returned back into the atmosphere during an eruption.
All right, that's enough of that.
The
Thought it would
remarkable
stop.
cycle is complete.
Okay. Hope you guys like my accent. Anyway, so here is a visual diagram of the heat rising, moving away, getting cold, sinking. And it says here due to density differences. So less dense things rise. That's how you get your ridge. And then as it moves away from the ridge, it gets colder and colder and denser, and it sinks back down. And that causes what's called subduction. So the hot things rise because they're less dense. The cold things subduct or dive back down because they're more dense. They come back again. Basically, boiling water moves through convection. This is just boiling magma. So on the bottom of your screen, it says lithospheric plates move with the convection currents in the asthenosphere, just like a raft will move with ocean currents. All right, next slide. All right, so the definition of a plate boundary is the meaning of two plates. This causes earthquakes and volcanoes. There are three types of boundaries: divergent, convergent, and transform. And this is a map of the boundaries. This is the map that you're going to be given on any test you take in my science class. All right, and we're going to go over how to read this map, and we're going to do a lab using this map. So how do we know where the plate boundaries are located? Well, if we actually mapped every earthquake and volcano and put like a little pin on the map for wherever they occur. Okay, here's an earthquake and volcano, put a pin, put a pin, put a pin. Well, what happened is they will map out the plate boundaries for us because all those earthquakes and volcanoes are clustered in zones. Okay, and those zones are where the different plates meet. So by mapping all the earthquakes and volcanoes, we were able to make the map of the plate boundaries. So that's the answer, by plotting the locations of the world's earthquakes and volcanoes. So we don't think New York is at a plate boundary. Okay, like here's New York. It's not at one of these boundaries that are on the bottom here on this key. So the reason we believe New York isn't at a plate boundary, well, you guys all live in New York. Are we concerned about earthquakes and volcanoes? No, not at all. Why not? Because we're not at a plate boundary. Okay, so we believe we're not at a plate boundary because earthquakes are very rare. Now, California is known for earthquakes. So if you know your geography, here's California, and the most famous fault in America goes right through it. It's called the San Andreas Fault. Now, fault is a crack in the crust where earthquakes occur. Okay, so look at all this here. This is all boundary, and it's surrounding the Pacific Ocean. See? And we give this a nickname. It's called the Pacific Ring of Fire. And if you were to actually measure and plot most of the world's earthquakes, they're going to fall around this region surrounding the Pacific. Now, if you look at the Atlantic coast, here, like from Maine to Florida, we don't really have earthquakes. From all the way through Brazil, through the southern tip of Argentina and Chile, down here, no earthquakes. This side they have it, this side they don't. Here, Spain, France, Great Britain, they're all on the Atlantic, no earthquakes. Okay, so they're not at a plate boundary. So what I have here is a couple links that are very helpful. I'm going to play this one first. This one's from the United States Geological Survey, which is probably the world's leading survey or site for natural disasters. And this is a wonderful site. What you can do is go to settings, and you can plot all the earthquakes wherever you want. So I actually want to go first to a world view. Excuse me. Of course. All right. Maybe I need to zoom to world. There we go. I want to go on a world view. So these are all the earthquakes that occurred in the past day that are a 2.5 and greater. All right. And look, they're all around the Pacific. This is the West. This is California. That's Washington State, Oregon. This is West Coast of Canada, Alaska. All right. Parts of Russia, all of Japan, Philippines, Indonesia, New Zealand. These are all around the Pacific. Okay. While the Atlantic, except for this little region right here with the country of Haiti, Puerto Rico, Dominican Republic, which is actually the same land as Haiti, there's not many earthquakes at all anywhere on the Atlantic. Okay. So let's take it a step further. Let's do 7 days and see what happens. Wow. So we got more. So these are 7 days of a 2.5. The 2.5 is very minor. Okay. You wouldn't really notice it. You might just think it's construction. So you wouldn't even realize there was an earthquake going on. Okay. So these are very sensitive machines called seismograph machines, seismogram machines that record the earthquakes. Now let's do 30 days. Let's just go through it. 7 days, all magnitudes. All right. I guess that was the same pretty much. 30 days. 30. Uh-oh. Continue anyway. Let's see what happens. Technical difficulties. Why wouldn't it be? Okay, show real-time data instead. All right, nothing's working my way. Okay, so these are 30 days significant. I think significant is considered, like if you put your cursor over these, it would give you a lot more information of the size. All right. And it would tell you like the depth. Here, so I'll bring one up. So if I click that one, that tells me on the side here that this was in Honduras. It was a 6.0. It was 55 kilometers northeast of Savannah, Honduras. And there was actually, see this? That means there was a tsunami warning. All right. It also gives me the depth. This was 10 kilometers deep. So this started 10 kilometers under the crust. Okay. And then the exact latitude and longitude are right here. Okay. And, you could play around with this if you wanted to know more about it. So this white one right here, that seems to be the biggest one. Let's click on that one. So this one also looks like it has a tsunami warning. So you could click on the tsunami warning center and it might tell you the size of the tsunami, if there was one, if there wasn't, if they're still concerned. All right. So this is a very useful site if you're really interested in exploring it more. Okay. I'm going to now go to the next one. Nothing's working properly. 30 days. Okay, here we go. So this is 30 days of 4.5 and over. So that's not considered as significant. But if you notice, you're really starting to map out specific areas. And if we let this go for years, all these red lines will be covered with dots. And that would be our plate boundaries. Okay. Let me go now back to the notes. Nothing's working interactively right now for me. Okay, so I'm back in the notes here. So this is the map of the plate boundaries. And these are 2 videos which show you basically what I was just describing. It just does it really fast. So I'll play them for you. Really missed the fun. I'll fast forward. I think you guys get the picture. Okay, so what you're seeing there now is where all the bright lights are. That's where the world's major earthquakes were. See how they're all around the Pacific? So if we start to plot these, you see, look here. So you really get, that's your mid-ocean ridge. It's more volcanic than earthquakes, so you don't get as bright of an area there, but there's minor earthquakes there. Okay. So this right here, when I'm tracing over, this would be called the African plate. Okay. And then this right here be the South American plate. Then you have another plate right here called the Nazca plate. See this little area right here? This is why you get some earthquakes in Haiti, in Puerto Rico. This is called the Caribbean plate. Makes sense? You can see this little triangle or diamond shape, sorry. Diamond shape. That's the Philippine plate. Okay. And this video is really the same thing as that one, just more on a map. Once again, play it on your own time if you want to really explore or dive deeper into this. I think the other site, the USGS site, that's the best one. And there's more to it. I would really take the time to explore it on your own. Okay. So here's the map that we're really going to be using over the next few classes. And this is what your lab's going to be on. So you're going to get this lab assignment tomorrow. And what it's going to ask you to do is trace the boundaries. So there's 3 major boundaries because things could move relative to something else in 3 major ways, right? What I mean by this is 2 objects can come together. We call that a convergent boundary. 2 objects can be going apart. We call it a divergent boundary. Or they could slide past one another. We call that a transform boundary. So right here, when my cursor's on, that's sliding past. That's what we have in California. That's a transform boundary. See here, where the arrows are moving away, that means they're diverging, separating. And that's everywhere where you have your ridge. See, Southeast Indian Ridge, arrows are moving apart. Right here, Mid-Atlantic Ridge, what are the arrows doing? They're moving apart. So instead of saying arrows are moving apart, we call it a divergent boundary. Instead of saying here that the arrows are moving or sliding past one another, so if you think the arrows are sliding past one another sideways, we call that transform. And if the arrows are coming together or colliding, well, that means converging. We call that a convergent boundary. So right here, this is India. It collided with the rest of Asia, and there's your convergent boundary. Okay, here. So here you would have convergent boundary. Right. So what you're going to be asked to do in the lab is to color in the boundaries. So basically, if I ask you to color this, I forget which colors I asked specifically. I think for transform, I remember I asked for green. So for every transform boundary, I'm going to trace that over with green. So anytime I see a single line, I'm going to go over it in green. and then whatever colors I'm asked. I'll review this tomorrow, all right, in tomorrow's lesson. All right, the last two slides I want to end the lesson with, and then I'll continue with this moving forward. So these notes are going to take a few days to really go through. You can read ahead if you want, just to enrich yourself, or you can wait for me. So this is the other part of the lab. So this lab is going to be two parts. You're going to color in the boundaries, and you're going to color in the plates. Okay, so this one, the plates are colored in. While in this picture, the boundaries are colored in. So that's really what you're doing tomorrow in the lab I'm going to put up on the Google Classroom. You're going to color in the boundaries. That's what you're seeing here. And you're also going to color in the plates. Okay? So that'll be your assignment for tomorrow. I'll explain it again in a little video. And then we'll finish the rest of these notes in a third video that I'll post later in the week. All right? I hope you enjoyed it. Have a great day.